A warm welcome to one and all. This is Dr. Sanoop, Assistant Professor, Department of Chemistry, Madanapalli Institute of Science and Technology. Today, I am going to discuss one of the important topic, the introduction of Raman spectroscopy. Actually, this lecture session I am planning to the graduates, those who are in chemistry or those who are in science and engineering streams. Okay, this lecture contains mainly what is spectroscopy and also what do you mean by Raman spectroscopy and its various applications. Okay, coming to the first slide here, you can see that one the definition of spectroscopy. Okay, it is very important to know what do you mean by spectroscopy. Actually, how will you define this spectroscopy? It is the study of interaction of electromagnetic radiation with matter. Here you can see that one three terminologies are there. You have to understand what do you mean by interaction, what do you mean by electromagnetic radiation, and also matter. That is very, very important. Okay, so we can discuss one by one. Okay, if you know the meaning of electromagnetic radiation and what do you mean by matter and what type of interaction you are expecting with this electromagnetic radiation and matter. Okay, the first of all we have to discuss the matter. Okay, so matter means you can see that one. Okay, we can define matter is a substance that has a mass and takes up space. Okay, which occupies it having some mass and occupies some space. That is called matter. But matter in chemistry, what we are mean actually is very simple: atoms or molecules. Here you can see that one oxygen atom, carbon atom, hydrogen atom. If the atoms are combining, what you can see here, oxygen molecule, carbon dioxide molecule, okay, like that, water molecule. So here in chemistry, what we are considering, the matter means what is that? Atoms and molecules. Okay, once we are considering only atoms, that is called atomic spectroscopy. Very simple to understand. If we are considering molecules, that is called the molecular spectroscopy. Okay, so I think you understood the meaning of the matter. What do you mean by matter? Either atoms or molecules. Okay, then coming to the second term, that is electromagnetic radiation, EMR. What do you mean by EMR? This is very important to understand. The EMR means it have the electromagnetic radiation means it have both magnetic and electric fields. Okay, and the propagation of direction all are in perpendicular with each other. That you can easily understand. Okay, and also each EMR, which means each electromagnetic radiation is associated with some energy also. How will you calculate the energy of electromagnetic radiation? It is very simple. That is E equal to h nu by the Planck's law or Planck's equation. What is E? Energy. H is actually, here you can see that one, E equal to h nu. That is the equation we are using. What is E? That is the energy, and h is the Planck's constant, and nu is the frequency of the wave. Okay, so based on the energy, what we can do, we can arrange the different electromagnetic radiation based on their energy, frequency, wavelength. Okay, here you can see that even that arrangement is called the electromagnetic series or spectrum. So here you can see that one different waves are arranged based on their decreasing order of energy. Okay, starting from gamma rays to long or radio waves. So what is the properties regarding gamma and X-rays? You know that one both gamma rays and X-ray they have high energy waves. If you are coming from the gamma rays, X-rays, and you can see that the UV. What do you mean by UV? Is ultraviolet. Then also you can see here one region is there that is visible, VIBGYOR, that we already studied in your primary levels. Okay, then you can see that even low energy waves, IR, infrared radiation. So what you can see here, we are arranging different electromagnetic radiation based on their frequency or wavelength, either increasing order or decreasing order. And also you should know that one as per the Planck's equation, E equal to h nu. You know that one. And also here energy is directly proportional to frequency. The same way, how will you connect the energy with the wavelength is very simple. E is equal to hc by lambda. What is lambda? That is wavelength. So you should know that one. The energy is directly proportional to frequency, and also the energy is inversely proportional to wavelength. That is a relationship you have to understand. Okay. So this is all about electromagnetic radiation. Okay, so here we are having different series of electromagnetic series radiations. So either we can arrange them based on their frequency or wavelength. So the next one that is very very important, that is the how these matter, as I already mentioned, that one, atoms or molecules. Okay, how this matter connected with this EMR, electromagnetic radiation, that is very very important. So here you can see that one, suppose one matter is there, but you can see that, okay, suppose some light is coming, okay, EMR was either IR radiation, either UV radiation, okay, whatever the radiation, okay, whatever the EMR. Okay, what happened? The molecule absorb the energy and it goes to higher energy level. That is called excited states. Okay, that is called absorption of the energy. Absorption. And also you can see that even once the molecule in the excited state, it will come to the ground state. That process is called emission. Okay, so here you can see that one is absorption of the energy and the emission of the energy. So based upon the interaction, so here one is absorption, other one is emission. So we can call it as absorption and emission spectroscopies. So this is also very very important. And coming to the next slide, you can see that even what type of interaction you can really see in the case of molecule. Okay, so I already mentioned that one. There are different EMR waves are there, microwaves and infrared, visible, ultraviolet, and also X-ray. There are different and waves are there, electromagnetic radiations are there. Suppose if I am considering microwaves, as you already know that one, in electromagnetic series, microwave radiation is having very less energy. So what about the frequency and wavelength? It is having very low frequency and higher wavelength. So what you can see here, if the molecule absorb microwave region, what you can see in the molecule, there is some molecular radiation, or sorry, the molecular rotation, some molecular rotation you can see there. But you can see that if the molecule absorb microwave region, in the molecule itself we can see that even some rotational change. The same way, what you can see, if the molecule absorb infrared radiation, what is infrared radiation? IR radiation. What happened? There should be some molecular vibrations like bending, stretching vibration, bending vibration. You can observe in the molecule also. Okay. The similar way, what you can say, if the molecule absorb ultraviolet, means UV as well as visible light, you can see that even there is some electronic or electron level transition or electronic transition. So you can easily understand that also. That is why we can call microwave spectroscopy is also called as rotational spectroscopy. Why? If the molecule absorb this microwave region, what you can observe there? There should be some rotational change in the molecule. The similar way, the infrared radiation. So the infrared spectroscopy is also called as vibrational spectroscopy. What is the reason for that one? It's very easy to understand. After absorbing the IR radiation, after absorbing the infrared radiation, what kind of change there? You can see there is a molecular vibration. That is why it is also called as vibrational spectroscopy. The similar way you can observe in the case of UV and ultraviolet. What is that? There should be some electronic transition. Here you can see that even some electronic transition is there. So that is why it is called electronic spectroscopy. So you can easily correlate with these terms. Okay. So moving to the next slide, what you can see here is very simple. Okay, we are directly starting to what is spectroscopy. Okay, we are already covered that topic. Then we are going to discuss what do you mean by Raman spectroscopy. So now you are able to express or you are able to define what is spectroscopy. What is spectroscopy? Spectroscopy, it is the study of interaction of electromagnetic radiation with matter. So you know what is matter, what is electromagnetic radiation, and also what type of interaction. Maybe it's a microwave region, what type of interaction? Some rotational change. If it is IR radiation, what type of interaction? Is a vibrational change. Okay, so that is an important aspect of spectroscopy. Then now we are moving to the another part, that is a Raman spectroscopy. Here you can see that even the Raman spectroscopy, it is the vibrational spectroscopy. So what type of interaction you can see that one is a vibrational spectroscopy. And also in IR spectroscopy you can see the vibrational change. But instead of absorption, what we are considering here we are considering scattering of light. Scattering. Okay, here they are correctly mentioned inelastic scattering. Inelastic scattering of light. Okay, you can understand the terms. It's very easy to understand. Suppose one molecule is there. You can here you can see that one diagram is there. It is showing okay both two types of scattering. First one is the Rayleigh scattering and second one is the Raman scattering. Okay, so I will explain what is Rayleigh scattering. It's very easy to understand. Okay, if your molecule is in the ground state, this black line you can see that even the ground state. You know that even most of the molecule you can see in the ground state at room temperature. So the population of the molecule in the ground state is high when you are considering the normal condition or room conditions or room temperature. Okay, so here what you can see here is a Rayleigh scattering. In Rayleigh scattering, okay, this is the frequency of incident light. You can see here is a frequency of incident light. Okay, and this is the frequency of scattered light. This one is the frequency of scattered light and this one is the frequency of incident light. And both the case what you can observe, both having same. Okay, the frequency of incident light and the frequency of scattered light both having same energy. So that is why that type of scattering is called a Rayleigh scattering. Once you are considering the Raman and Raman scattering, okay, here you can see that even two types of lines are there. What are the two types of lines? Anti-Stokes and Stokes. Okay, Stokes line. Both together, what we can call is Raman scattering. Okay, okay, once I will discuss the anti-Stokes line. Okay, here you can see that one, the green one is the incident light frequency. Incident light means whatever the EMR, whatever the electromagnetic radiation we are using. Okay, what about the blue one? This is actually nothing, this is the scattered light. What you can observe here, the incident light frequency or energy lesser than that of the scattered light. You understand? So what is the meaning? Here, the energy of or the frequency of scattered light somehow very higher as compared to incident light. Okay, so what about this case? This case you can see that one the incident light frequency is higher than that of scattered light frequency. Okay, so here the incident light in Stokes lane, what you can observe, the incident light frequency somehow is higher than the scattered light frequency. And what about anti-Stokes? The incident light frequency is lower than the scattered light frequency. So here, and also one thing you can observe here, actually the transition is happening from somehow is high excited level or higher energy level. So what about here in Stokes lane, what you can observe, the transition is happening from the lower energy state. The lower energy state you can observe the transition. Okay, so I already mentioned that one, the most of the molecule at room temperature you can see in the ground state level, Okay, so it is very simple. Okay, here we are mostly considering Stokes lane, Stokes Raman scattering instead of anti-Stokes. Why? Well, the answer is very simple. You can see that even in Stokes lane, the transition is happening from the ground state, and I already mentioned that even in the ground state, you can see maximum number of molecule. That means the population of molecule, the population is very high. According to Maxwell-Boltzmann statistics, what we can say, if the population is high, what about the intensity? The intensity is also high. The same thing here, what you can see, this is this transition in anti-Stoke, the transition is happening from somehow is higher energy level. Okay, so you know that one, that is somehow the molecule population. The population is somehow is very low. So what you can observe there? You can observe, okay, very low intensity anti-Stokes lane. So that is why we are considering Stokes lane instead of anti-Stokes lane. Okay, so normally we are taking Stokes Raman scattering. So what is the reason for that one? It is only because of the intensity factor. The Stokes having higher intensity. So this is actually Raman spectroscopy, all about Raman spectroscopy, and also you should know that one, the Raman spectroscopy, our famous Indian scientist Sir C.V. Raman, who invented in 1928, that is called Raman effect, and also he got a Nobel Prize in 1930, the first Asian who got Nobel Prize in physics. That is very important. So as an Indian, you have to proud of this also. Okay, so what we can do here, the Raman scattering and Rayleigh scattering. Okay, you have to get a better idea what is the difference between Rayleigh scattering and Raman scattering. Okay, coming to the next slide is very important, as I already mentioned that one. Okay, every spectroscopy there should be some instrumentation. Instrumentation means what is how these all this thing like the light source and also the probe optics. Okay, I will explain what is probe optics, detector, how they are aligned. Here you can see that one in every spectroscopy, whether it is IR, Raman, UV, whatever spectroscopy, there should be a light source. For example, in the case of IR spectroscopy, we are using some mercury lamps for IR radiation. For in the case of UV visible light, what we are using UV visible spectroscopy, what we are using? We are using for UV light, we are using either hydrogen or deuterium lamps. For visible light, we are using tungsten lamp. The similar way in Raman spectroscopy, we are using laser light source. You know that one? Lasers are monochromatic in nature. Okay. The second part is there. You can see here that is called probe optics. Probe optics. Okay, that is very very important. Here you can see that one. Here so many optical components are aligned here. Okay, lens, beam splitter, filters. Okay, so you have to understand what is this part. Okay, that's all together. It is called probe optics. Okay, here you can see that one filters, lens. Okay, and beam splitter. So many optical components you can see in this case. Okay, so what is the meaning of this thing? Yes, it's very easy to understand. Okay, lens, as you already know that we can use convex lens. That is the purpose, focusing the light. Okay, lens, you know very well. And what about beam splitter? The term itself said that, what is that? It splits the light into two parts. Okay, here you can see that one. Suppose light is coming in this direction, what you can see there? Okay, the light split into two parts. The one part that is called RT. The beam splitter is called RTBS, beam splitter. What is the meaning of RT? R means reflection, T means transmission. Here you can see that one. Okay, some of the light is, what is that, reflected, and some of the light is transmitted. That is the meaning. Okay, for example, I will tell one example. Suppose I am taking RT 50 50. What is the meaning? RT 50 50 means the beam splitter has the property of 50% of the light is reflected and the remaining is transmitted. That is the meaning. Okay, so similar way we can use RT 70 30, RT 30 70. Okay, we can use various beam splitter according to your applications. The similar way, here you can see that in filters. What is the purpose of filter? Okay, suppose I want to eliminate some area or some frequency, some wavelength, particular wavelength. That purpose we are using filters. You know, and also we are having long pass filter, short pass filter, notch filter. There are so many filters are available. And the same thing, the last one you can see that one detectors. That is very very important. Okay, normally what we are using CCDs and also PMT, photo multiplier tubes, that we are using as a detector. Okay, so finally what we can see, the detector detect the signal and you are getting a Raman spectra like this. This is actually the Raman spectra of creatinine powder we took in 785 nanometer 785 nanometer laser source. We can see here. Okay, so that is very very important. You should know what are the instrumentation parts of Raman spectroscopy. So this is the general aspect only. So every spectroscopy is associated with some light source, probe optics, and detector. So in this case, light source, I already mentioned that one. We are using lasers. Okay. So according to the application, we can change which laser source we want. For example, we can use high energy laser source if you are considering some material applications. In the case of biological application, you know that even tissue, cells, if you are considering some biological application, we have to use some low energy lasers like 785 nanometer, and also maybe we can go to the NIR region also, 1064 nanometer. So low energy lasers. I'm just telling only about the wavelength. Higher the wavelength, lower the energy. I already mentioned in the previous slide. Okay, so here you can, according to the application, we can decide which laser I want. Okay, and also the probe optics, okay, and detectors. That is very very important. And we are keeping our sample here only, and from the scattered signal, what you are getting? You are getting the vibration of the molecule from the scattered light. You are getting the vibration of the molecule, and finally you will get a spectra like this. This is the creatinine powder. I already mentioned that one. Here peaks you can observe. This peaks is actually nothing. It is actually vibrational changes in the molecule. For example, I will tell, okay, In before the 1000, you can see one big peak. That is actually for the creatine molecule CC vibration, C double bond C vibration, and saturation, such kind of vibration you can observe in the case of Raman spectra. So what you are exactly getting the Raman spectra symbol, we are getting the vibrational information. Okay, the fingerprint information. We are getting the fingerprint information. And also here you can see that one, we are plotting the Raman spectra with the Raman shift against the intensity of the peak. Okay, so what I mean by Raman shift is very easy to understand. Okay, which light source or which laser we are using. Okay, 532, 633 is there, 633 is available, 785 is available. So according to this is the shift from the later that light source. Which light source you are using? Lasers. Okay, so actually this is a shift in the wavelength between what you are exactly where you can see the peak with respect to your light source wavelength. There is actually some difference you are observing in the Raman spectra. That is why it is called some shift, Raman shift. Okay, then why we are more focusing about Raman spectroscopy? That is also very, very important. Okay, so what are the most advantages of Raman spectroscopy? We can see here, what is that? Raman spectroscopy is first thing you can see, this is a non-destructive technique. That I already mentioned, in the previous slide. Okay, according to our application, we can choose which laser source I want. For example, if I am planning to conduct some experiments in the case of biological sample, what we have to use? Low energy sources. Regarding the material, we can use high energy light sources, no problem. So, is a non-destructive in nature. And what is the second one? It needed minimum or no sample preparation requirement. Okay, as such, we can do the measurement. Whether it is a solid form or liquid form, we can go and do the measurement. And also, very small amount is needed for the Raman spectral analysis. Okay, and coming to the third one, provide fingerprint information. What is that? That I already mentioned. Okay, we know that one from the Raman spectroscopy. What we are getting? We are getting the vibrational information. Vibrational information. So we are getting the fingerprint information regarding where the CC vibration is happening. We are all discussing about molecules. Okay, so where is the carbon-carbon single bond vibration, carbon-carbon double bond vibration, where you can see this fingerprint information. All this information you can take from these Raman spectra. That is, we are getting the fingerprint information. And also you can see that even it is rapid, sensitive, and cost-effective analysis. What is the meaning? That I already mentioned that one. In for taking one Raman signal or one Raman spectra, it around take 1 to 10 seconds according to your integration time. How much integration time you are giving? Okay, so that is actually determining how much time we need to take one Raman spectra. So that's why it is called a very rapid. Okay, and it's cost effective also. Here nowadays in the market we can see the portable Raman spectrometer. It's around 5 lakhs to even crores are available. According to the resolution, sensitivity, everything is a factor. The similar way you can see that even it is suitable for on-site application. Yes, there are so many portable devices are available now. Even though a box model is there, box model, you can see in the market. So we can use the application of this Raman spectrometer for various on-site application. The similar way is it is having high design flexibility. What is the meaning? It's very simple to understand. The scattering process is all about Raman spectroscopy is all about inelastic scattering. The scattering process is actually 360-degree process. So that make the instrument having high design flexibility. We can make the instrument in various design. So that make the instrument in high design flexibility. And the final point that is very, very important. That is because in IR spectroscopy and Raman spectroscopy, we are getting the vibrational information. But why we are more focusing Raman spectroscopy? It is because of, you can see that even there is a minimum interference from the water. Because in the case of Raman spectroscopy, if you are applying some biological application, what you can see there, we know that in our body is most of the content is water. We are having around 70 to 80% in our body is water only. Okay, so if you are using Raman spectroscopy, there is a minimum interference from the water. But in the case of IR spectroscopy, it is not like that. Both the spectroscopy, we are getting the vibrational information, but More importantly, we are using Raman spectroscopy instead of IR in the case of biological application, because water molecule or water is highly IR active. So it will interfere the remaining experiment, the remaining outcomes also. So that is very, very important. This point is very, very important. Why Raman spectroscopy having that much importance in the field of biomedical applications? This is the only reason. Minimum interference from the water. Okay, then coming to the applications of Raman spectroscopy, you can see that various applications are there. Here, Raman spectroscopy having various application. We can use in the beverages, pharmaceutical, narcotics, explosive detection of explosive, identification of chemicals, imaging and diagnosis, especially for cancer detection. Okay, cancer diagnosis. Okay, the screening. All these things we can use the applications of Raman spectroscopy, and also in the field of food products. Okay, detection, adulteration detection, we can use this Raman spectroscopy. Okay, so here I mentioned so many applications. So I will I will explain the application of Raman spectroscopy by taking a specific example in the case of food. Okay, so this experiment actually we performed in our laboratory during my PhD period. Here you can see that one. Okay, we determined the important quality parameter of edible oil. You know that edible oil, we are using different edible oil like coconut oil, sunflower oil, palm oil. There are so many edible oils are available in the market. So using Raman spectroscopy, okay, we developed a method, a novel methodology for the detection of some of the quality parameter of edible oils. Here you can see that even what is the quality parameter. Here iodine value is there, okay, saponification value is there, acid value is there, and peroxide value is there. Okay, so using Raman spectroscopy, okay, in this experiment, what is our aim? We are going to determine the iodine value. That is one of the most important quality parameter of edible oils. So if higher the iodine value, a symbol, okay, I will give a simple explanation. If higher the iodine value, you can see the edible oil, the oil having higher unsaturation. Unsaturation. If lower the iodine value, you can see a more amount of saturation is there. Okay. So in this experiment, what we are planning, we are going to determine the iodine value of different brands and different types of edible oils. Okay. So for that, nowadays actually the method actually in the some state and national level laboratories they are using this conventional method, the titration methods for the determination of iodine value. You know that one. Some of them perform some of the titration near intermediate level. Okay, you know that one. It will take around 2 to 3 hours, including the sample preparation. Okay, here you can see that one. The titration method. Normally, we are using the conventional method we are using for the determination of iodine value. But what we are trying, okay, we have to develop a new method that is based on the Raman spectroscopy for the detection of the based on the Raman spectroscopy for the detection of the iodine value of different edible oils. Okay, so for that purpose, we took some model system. Here you can see that one model system. Here I took CO and SO. CO and SO is very simple. It's a abbreviation only. It's actually coconut oil and sunflower oil. Okay, why I choose this one is very easy to understand. Coconut oil, it having very high level of saturation content. Saturation means chemistry point of view, we can say that even the single bond content. So what about in sunflower oil? It is having higher unsaturation level. Higher unsaturation level. So what is the meaning? It is having higher double bond content. That you can say. Okay. So I already mentioned that even in Raman spectroscopy analysis, we are getting the vibrational information, the fingerprint information. Okay, definitely we will get the information regarding saturation, single bond, as well as the unsaturation, double bond information. Okay, and what is iodine value? It is the measure of total unsaturation present in the oil or edible oil. Okay, what is it? Is the total, the degree of total unsaturation present in the edible oil. So, from the spectral information, we can easily take the unsaturation to saturation level information. It's very easy. Okay, so what we did here, you can see that one we are coconut oil. Coconut oil, I already mentioned that one. It is having very low unsaturation level, and sunflower oil having higher unsaturation level. Okay, sunflower oil having higher unsaturation level. So we took its combination also. Okay, so what we can see lower to higher, we will get a range of iodine values also. For example, palm oil is having around 64. Okay, coconut oil having iodine value of 10. Okay, less than 10, and sunflower oil having iodine value of 150. Okay, you can see that one. Suppose I am mixing coconut oil with the sunflower oil, I will get a range of values. That is also fine. Okay, so the same way, some of the oil like gingerly oil, palm oil having the iodine value between 10 to 150. So we can analysis that type of edible oils also. So using this method, around 20 edible oils we were analyzed. Okay. So what is the main thing? Here you can see that one. In the second graph, you can see that one. Okay, the peak is there. Here, the peak. Here you can see that this is the pure coconut oil. The red graph is showing the pure coconut oil. Okay. Once you are mixing or once you are adding the 20 percentage of sunflower oil, the second one, the blue one, here you can see that even the peak intensity is increasing. What is the meaning? Actually, the peak at 1658 is corresponds to unsaturation level. That I already mentioned that one iodine value, which is the degree of measure of unsaturation level. Iodine value. Okay. So here you can see that even if I am increasing the concentration of sunflower oil in the coconut oil, here the intensity of unsaturation is continuously increasing. Or we can say that even linearly increasing. The same way, here you can see that even the peak at 1442, 1442, that is actually for saturation level. So what you can observe here, in the peak at 1442 is around, it's almost same for all. Okay, so what we did here, we took a ratio between unsaturation to saturation level, a ratio between unsaturation to saturation level, and we made some algorithm using some software. You know that so now we are adding some machine learning softwares also, ML softwares. Okay, so we develop one software, or we can say that one GUI, graphical user interface, in LabVIEW with the help of LabVIEW. Okay, LabVIEW is one of the software we are using for making some small GUI, graphical user interface, like your mobile phone screen. Okay, so we made some software regarding this one based on the Raman spectral analysis of these different types of oil. And finally, what is our result is very important. Okay, as I already mentioned that one, in the case of conventional method, that is we are using titration method, it will take around 2 to 3 hours for the analysis. Okay, but in our case, in our developed case, you can see that one we will take around 2 minutes for the complete analysis. Okay, that is good. Okay, we can use this a portable system only. We did all the experiments in the portable system only, so we can use the same system for various on-site analysis. So that is the one of the application. That is one of the important applications of Raman spectroscopy. The similar way you can see various applications of Raman spectroscopy in different fields, especially in the cancer diagnosis. Nowadays, it has that much importance in the case of cancer diagnosis. Okay, especially the screening of cancer cell, whether the patient having cancer or not. We are doing the screening with the help of some multivariate or chemometries, multivariate analysis like PCA, principal component analysis, PCR, principal component regression. Okay, there are so many methods are available. So these are the basic things regarding Raman spectroscopy. So in this lecture, what I'm meaning, all things I'm explained regarding the positive aspects of Raman spectroscopy. You know that one, every system there should be some disadvantages. Okay, so the next lecture, what I am planning, yes, exactly, the Raman spectroscopy also having some limitations. Okay, so how we can overcome that limitation? So what are the limitations are there? So how we can overcome? So we will discuss in the next lecture. Thank you very much.